Namaste. Welcome to the lecture series on the subject Basic Thermodynamics. This is module 4 in their part 2, Pure Substances. Lecture number 1. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So the contents for this topic are Introduction to Pure Substances, Phases of a pure substance, compressed liquid, saturated vapor, and superheated vapor. A pure substance is one that has homogeneous and invariable chemical composition. It may exist in more than one phase, but the chemical composition is same in all phases. See, there is a major requirement for a substance to be called as the pure substance. Irrespective of the phase, it should have the same chemical composition. Liquid water, a mixture of liquid water and water vapor, and a mixture of ice and liquid water, all are pure substance. Because liquid water, it is H2O, water and water vapor, that is also H2O, ice and liquid water, that is also H2O. Ice is also H2O, liquid water is also H2O, vapor is also H2O. So that is why in the pure form as well as in the mixture form, so it has the same chemical composition. On the other hand, mixture of liquid air and gaseous air is not a pure substance, because of the composition of the liquid phase is different from that of the vapor phase for the air. So liquid air is a different composition, gaseous air is a different composition. Now you can see the phases of a pure substance. So generally, we consider three phases, that is solid phase, liquid phase, and the gaseous phase. So the first figure here shows the molecular arrangement in the solid phase. Second diagram shows the molecular arrangement in the liquid phase, and third one in the gaseous phase. The molecules in a solid are arranged in a three-dimensional pattern that is repeated throughout. So I am not going to explain much about this because you studied it in some other subject, right? Because of the small distances between two molecules in solid, the attractive force of molecules on each other are large and keep the molecules at fixed position. So this is the main reason for the molecules to be in the fixed position, that is because of the strong intermolecular force of attraction. At high temperature, these intermolecular forces are overcome and the group of molecules break away. So this is the beginning of the melting process. So when you supply heat to solid, it melts into liquid. So what is the reason for that? So here the intermolecular forces are broken away and the molecules are being separated, or the forces becomes less. The molecular spacing in the liquid phase is not much different from that of the solid phase, except the molecules are no longer at fixed positions relative to each other and they can rotate and translate freely. So this is the difference between the solid phase and the liquid phase. Here, though the molecular spacing is almost same, but the molecules are no longer in fixed positions. That means they can move relative to each other, they can rotate and they can translate. In a liquid, the intermolecular forces are weaker compared to the solids, but they are still stronger when compared to gases. In gaseous phase, the molecules are far apart from each other and molecular order is non-existent. So there is not definite order for the molecules. So they are far from each other. So gas molecules move at random, continually colliding with each other and the wall of the container they are enclosed in. So gas molecules always move randomly, colliding with another molecules as well as with the wall of the container. Molecules are at a considerable higher energy level than they are in the solid and liquid phases. So because of the absorbing of energy, so the molecules in the gaseous phase are at higher energy level than the solid and the liquid phase. So it must release a large amount of energy before it can condense or freeze. So that is why if a gas is condensed into liquid, so it will release large amount of energy. Similarly, when it is freezed into solid, further it releases some amount of energy. Now let us study the phase change process in a pure substance. Now here first let us understand some definitions in this lecture. So then about the phase change process we will study in the next lecture. Okay. Now let us begin with the definition of compressed liquid and saturated liquid. Water existing in the liquid phase is called compressed liquid or a subcooled liquid. It means that it is not about to vaporize, means it is not ready to vaporize. So anything below vaporization temperature, so that is called as the compressed liquid or the subcooled liquid. Now here all of you should know that the temperature at which the vaporization begins also depends on the pressure. So don't have the impression that a particular substance or liquid will have one vaporization temperature. No, it purely depends upon the pressure. Okay, so at a given pressure, if the temperature is just below or the temperature of the boiling point or the saturation temperature, so then we call it as the subcooled liquid or the compressed liquid. That is why you call it as it is not about to vaporize. You can see here it is not about to vaporize. So a liquid that about to vaporize is called as the saturated liquid. Means because here the boiling point has been reached. Means any further addition of heat, it will start converting liquid into vapor. So a liquid that is about to vaporize. So any addition of heat will transform liquid into vapor. So that is called as the saturated liquid. So here are two terms, compressed liquid and saturated liquid. Now a compressed liquid is characterized by these parameters. So the pressure should be more than saturation pressure for a given temperature. Then it should have less temperature than the saturation temperature at a given pressure. So you see I am talking about the compressed liquid. Specific volume should be less than Vf at a given pressure or temperature. Internal energy has to be less than Uf, that is internal energy for saturated liquid at a given point pressure or temperature. Similarly, enthalpy also should be less than the enthalpy at the saturation point. Here HF, UF, VF, all these things are the values of enthalpy, internal energy and specific volume at the saturation point. Saturation means point means it is about to vaporize, that point. Okay, so the values of these quantities should be less than the value at the saturation point. Okay. Now let me explain the characteristics of a compressed liquid with the help of this table. So this is what we discussed in the previous slide, the condition for a substance to be called as the compressed liquid. So pressure has to be higher than the saturation pressure. Now at a given temperature, okay, I would have used the temperature table A2, but let me explain here itself. So let me take this temperature 135.54. So at this temperature the saturation pressure Psat is 3 bar. So you see Psat is 3 bar at 135.54 degrees Celsius. Now the given pressure, if it is more than this, like 3.1, 3.2, 3.5, 4, all these pressures, so at these pressures, right, pressure more than 3, greater than 3, because saturation pressure is 3 at 135.54, then we call it as compressed liquid. The reason is at these pressures, look at the saturation temperatures, so they are higher, but the actual temperature is less. That means it's not yet reached the saturation point. The actual temperature is 135.54, which is less than the saturation temperature corresponding to these pressures. That means it is not yet reached the boiling point. So that is the meaning of the compressed liquid. Now if I take the temperature here, it should be less than T saturated at a given pressure. Now let me take the pressure as 4 bar. So at 4 bar the temperature T sat is 143.63. So T sat is 143.63 whereas P is 4 bar. Now the actual temperature T should be less. That means temperature, if it is less than 143.63, so then we call it as compressed liquid. Now it is very clear, because at 4 bar the boiling process or the conversion of liquid into vapor will begin at 143.63. Now I am taking the example of water because this table is the steam table. All of you should understand. So I am talking about water now. So it is 143.63. If the temperature is less than that, that means it's not yet reached the boiling point. So that's what you have to understand. Okay. So then we call it as the compressed liquid. So temperature has to be less, whereas pressure has to be more than the saturation values at the given pressure and temperature respectively. Now coming to the specific volume, so V should be less than Vf. Now let us have the column Vf here. Okay. Before that, all of you should know the steam tables. So if you have thermodynamic data handbook, what I am using is the thermodynamic data handbook by BT Nijaguna and BS Samaga. So that is with me. So I can show you. So this is the thermodynamic data handbook which I am referring. Okay. Now this is a scanned page of that book. So in that A1 table, first column is pressure, second column is saturation temperature. This is the specific volume of the saturated liquid. This is the specific volume of the saturated vapor. This is the enthalpy of the saturated liquid. This is the latent heat of evaporation or the enthalpy during the phase change. This is the enthalpy of the saturated vapor. Similarly, entropy values at these three conditions, that is the saturated liquid, phase change and the saturated vapor. So one more thing you should know, HF plus HFG is always equal to HG. Right, now you see if you add these two, so you will get the same value. So here also these two, HF plus HFG is equal to HG. So similarly here also SF plus SFG is SG. That I will explain better when I take up the phase change diagrams. Okay. Now just before proceeding, I just explained you about this table, because without knowing this table, so it is difficult to understand. Now let me come to this third point. Specific volume should be less than Vf. Now what is Vf? So this Vf is nothing but the specific volume of the saturated liquid. That means which is about to vaporize. Saturated liquid which is about to vaporize, right? So at that point, because you see when you heat water, so there is small change in volume, okay, small expansion. But when it goes to phase vapor phase, so there will be this volume expansion is very much noticeable, but here it is very small. So here, so these are the specific volume. Specific volume means it is meter cube per kg. So volume occupied by 1 kg of the liquid water, okay, because it is a saturated liquid now, it is in the liquid phase. So here these volume values indicate that if this is reached, the liquid is a saturated liquid. Suppose if it is not reached, that means if the given specific volume is less than these values, then as it is mentioned here, so then it is called as a compressed liquid. So V should be less than Vf at a given pressure or temperature. Similarly, internal energy, okay, this table you don't have the internal energy column. So but from this table, if you take the values of specific volume and enthalpy, see this is the enthalpy here. So enthalpy similar to specific volume and internal energy also should be less than value at the saturated liquid point, that is HF. So then we call it as the compressed liquid. So here to find out U, you can use the formula U is equal to H minus PV. Suppose if you want UF, okay, if you want UF here, UF is nothing but HF minus P into Vf, because P is the pressure, so that is no suffix will come for that. But for this is nothing but UF is equal to UF. Similarly, you can find out UFG, that is HFG minus P VFG. UG is nothing but HG minus P VG. So this is how you have to make use of this table to find out the internal energy, specific internal energy, though it is not there in the table. Okay. Now let us discuss about this phase change process, or let me explain about the phase change process. For that, consider a piston cylinder device containing liquid water at 20 degrees Celsius and 1 atmospheric pressure, as shown in figure, this first figure. This is called as state 1. Under these conditions, water exists in the liquid phase and it is called as the compressed liquid or subcooled liquid, because you know that at 1 atmospheric pressure, so the boiling temperature is 99.63 degrees Celsius. So till then it is a compressed liquid. Now heat is transferred to the water until its temperature rises to 40. As the temperature rises, liquid water expands slightly, so its specific volume also increases. So that also you should know, as the temperature is increased, so volume also increases slightly. To accommodate this expansion, the piston moves up slightly against the constant atmosphere pressure of 1 bar, because piston is cylinder is enclosed or fitted with the piston, so the piston moves up slightly against the atmospheric pressure. So that is why we are calling it as heating water at 1 atmospheric pressure, because the pressure exerted by the piston is 1 bar. And water is still in compressed liquid state since it has not yet started to vaporize. Very important point to be noted. Now, as the more heat is transferred, the temperature keeps rising until it reaches 100 degrees Celsius. That is called as the state 2. Here you can see. So this is a state 2, right, where still atmospheric pressure is atmospheric 1 atmospheric and temperature is 100 degree Celsius. Okay, there is small variation in the diagram. Okay, so this volume has to be more than this volume. Okay, this volume is less, this volume is more. Okay, it's diagrammatic variation. At this point, water is still liquid, but any addition of heat will cause some liquid to vaporize. You see, this is called as the saturated liquid. So at 100 degrees Celsius, okay, so at 1 atmospheric, okay, 1 atmospheric 1.013. So sorry, I told you 99.63 previous slide. So that is in fact actually that is at 1 bar pressure, okay, not 1 atmospheric. So at 1 atmospheric, the boiling point is 100 degrees Celsius, correct? Okay. So at this point, at 100 degrees Celsius, when the water just reaches 100 degrees Celsius, till then we call it as compressed liquid. But when touches 100 and any further addition of heat, so water starts to vaporize or liquid starts to vaporize. So then it is called as the saturated liquid. So a liquid that is about to vaporize is called as saturated liquid. I hope it is very clear now the difference between the compressed liquid and the saturated liquid. So we took water at or liquid at 20, 40, so up to 99.9999, so it is a compressed liquid. So when it reaches such as 100, then at 100 any further addition of heat, it starts vaporizing. So that point is called the saturated liquid. Now here this 100 is depending on the pressure. Now for atmospheric pressure it is 100 degrees Celsius. For any other pressure this temperature is different. So that you have to check from the data and book. Okay. Now coming to the saturated vapor and superheated vapor. A vapor that is about to condense is called as saturated vapor. So saturated means here, now previously I told that saturated liquid which is about to vaporize. So if I continuously supply heat to that saturated liquid, so it gets converted into vapor until the last drop of this water molecule also gets converted into vapor. So then it is called as saturated vapor. So at saturated vapor there is no liquid particles or droplets at all. So complete conversion of liquid to vapor, so that is a saturated, but at the same temperature of saturated liquid only. So you know that during this phase change process there is no temperature change, also there is no pressure change. So phase change process, the moment saturated liquid starts vaporizing and completely gets converted into saturated vapor where there is no liquid particle, so this length or this process, that pressure remains constant, temperature also remains constant. That means saturated liquid at 100, you can see here, right? Now it is partly vaporized here, partly is a color change, partly it is liquid and partly it is vapor, till it is completely vapor. You see here there is no liquid. But look at the temperature and pressure, both 1 atmospheric and 100 degrees Celsius and 1 atmospheric 100 degrees Celsius. So this is actually mixture. It is not just beginning of the vaporization, because already some vapor is there. You can see. You see some volume already vapor is there. It's a mixture. So till you see now, then it goes this part, water quantity becomes less and less. Here you see there is no quantity of water. So this state 4 is called as saturated vapor. So here vapor that is about to condense. Now now it is 100, you see the temperature is here also it is 100. If it becomes bit less also, immediately it starts condensing to, actually it is not temperature becoming less, because at that temperature itself it starts condensing. But the only thing is you have to start removing the heat. You have to start removing the heat. Similarly, at 100 when the vaporization takes place, so there also it's not actually the increase of temperature, so we are adding heat. So any addition of further heat, so that is utilized only to convert liquid to vapor. So same heat which is required to vaporize will be removed back when this vapor is condensed back to liquid. So I hope it is very clear now. So from compressed liquid, it reaches the saturated liquid where it is about to vaporize. Any addition of heat further will not result in increase in temperature or increase in pressure. Rather, it will be utilized to convert liquid to vapor, right? And similarly, then it reaches the saturated vapor state. So at saturated vapor state, any removal of heat will not decrease its temperature or pressure. Instead, the vapor starts getting condensing into liquid. Okay. Now, if you supply heat further at the same pressure, now you can see the temperature goes beyond 100 degrees Celsius. So if it goes 100.1 also and anything above 100 also, so then it is called as the superheated vapor, because if a superheated vapor will not condense easily, which is not about to condense. About to condense means a removal of small quantity of heat or reduction in temperature, because 300 degrees Celsius, if you reduce to 299, it won't condense. 200, no, it should reach 100 first. Further at 100, if you remove any heat, then it starts condensing. So a superheated vapor is a vapor that is not about to condense. So these are very, very important terms to be understood in order to understand this pure substance topic. Okay. Okay. Now let us study the characteristics of superheated vapor with the help of this table. Okay. So same table I am using. So a vapor can be called as superheated vapor if its pressure is less than saturation pressure at a given temperature. Now let the given temperature, let us take it as 135.34, same value. Pressure is, saturation pressure is 3 bar. So P sat is 3 bar at 135.54. Now the actual pressure P should be less for superheated vapor. So that means let me take the pressure as 2.5 bar. Now at 2.5 bar, the temperature of the saturation temperature at 2.5 bar is 127.43. So actual temperature is 135.5 bar. You see, actual temperature is 135.54, for which saturation pressure is 3 bar, but actual pressure is 2.5 bar, for which saturation temperature is 127.43. So the actual temperature 135.54 is more than the saturation temperature. So anything more than saturation temperature, so that is called as the superheated vapor. That means here the actual pressure should be less than the saturation pressure at a given temperature. So you have to understand it very carefully. Okay. So in the first instant you may not be able to understand. So slowly and steadily analyze. Sit calm and analyze, then you will understand. So also for a given pressure, let me take this 4 bar, the temperature, given temperature should be greater than the saturation. Okay, this is clear, easy to understand. So here at 4 bar, the saturation temperature is 143.63 degrees Celsius. If the actual temperature is more than this, then surely it should be superheated vapor. Similarly, you have one more column here, that is for the volume, specific volume of the saturated vapor. This is for saturated liquid. This is for saturated vapor. So I will explain you this in the PV diagram as well as pressure volume, temperature volume diagrams. Okay. So here, if this volume, this is the volume attained by the liquid, or here this is for steam, in fact saturated steam, okay, saturated steam, that is saturated vapor. This is the volume attained by the water at saturated vapor point. Now if the volume increases further, if the specific volume is more than this at a given pressure or temperature, anything you can take. These three quantities you can take it at any pressure or temperature. Then so it is called as the superheated vapor. Similarly, the internal energy also should be more than Ug value. Enthalpy also should be more than the enthalpy at the saturation point. Then we call it as the superheated vapor. So just try to go through the tables, try to understand this point. Okay. So with this I conclude this lecture number 1 of this pure substance and I will continue with in the lecture number 2 about the various property diagrams during phase change process. Till then, thank you.